වාණිජ, විද්‍යා, කලා, ගණිත, තාක්ෂණ වේදය, විෂය ධාරාවන් වල සියලුම විෂයන් සඳහා දැන් නැනපවුර YouTube channel එක ඔස්සේ නැරඹිය හැක.
ආයුබෝවන් හැමෝටම අද අපිත් එක්ක සම්බන්ධ වෙලා ඉන්න හැමෝම ආදරයෙන් පිළිගන්නවා. ඒ වගේම කියන්න ඕනේ අද ෆිසික්ස් ඉංග්‍රීසි මීඩියම් සෙමින එක තමයි පැවැත්වෙන්න යන්නේ. අද අපිත් එක්ක එකතු වෙලා ඉන්නවා අපේ ආදරණීය ආචාර්ය සුරේෂ් වෙන්නකෝන් සර්. ඒ වගේම කියන්න ඕනේ මතක් කරන්න ඕනේ අපේ ප්‍රභාත් නලින්ද සර්වත් කියන්න ඕනේ අද දේශනේ වරුණාම අපි YouTube එකේ comment section එකේ ප්‍රශ්නයක් යොමු කරනවා. ඔයගොල්ලන්ට පුළුවන් උත්තරේ කමෙන්ට් එකක් විදිහට යොමු කරන්න. එහෙනම් මේ ආදරණීය ආරාධනය අපේ ආචාර්ය සුරේෂ් වෙන්නකෝන් සර්ට. අයිබෝන් සර්.
Ayuvan. Good morning, my dear students. Today, as it was told, I'm going to discuss viscosity. Here, I'm going to discuss the theory in brief, and you will be able to take down some notes during the lesson briefly. So be prepared for that. And then during the lesson, you can ask any question you have regarding the theory. And those who are in the those who are connecting with us in the Zoom, you can send your questions to the chat, and then I can answer them. And at the end of the lesson, I'm trying my best to do a little problem, but I don't know whether the time permits. Then all in all, I'm trying my best to cover all the syllabus during this part. Okay. But I think you can see the board now. So viscosity is our topic today, and to understand what the viscosity is, because the word viscosity is not familiar for most of us, because viscosity is not a general term used for something, but it's a technical term. Okay, so I'm going to give you a little task. Let's think of this. I'm going to give you water, second coconut oil, and three bee honey. Okay. Then, if I ask you to pour these three liquids to a ramp like this at the same time, and just think of which liquid will reach the bottom first. So I think there is no doubt all of you will agree that water will come to the bottom first. Okay, and then what will take the second place? Then somebody sometimes may have a doubt, but really it will be coconut oil, because coconut oil. Now if I ask, if you think of the reason behind why coconut oil comes first before bee honey, then most of you can answer it as because bee honey is thicker than the coconut oil. Okay. Then if we think of the reason behind coming water first and then coconut oil, then bee honey at the last, then it is not the density of water, density of the liquid, because water has high density than the coconut oil, and bee honey has the highest density, but it is coming at the end, at the last. But the least density belongs to the coconut oil, but it is coming second. Therefore, the mass or the density has no connection with this, right? Then, if you think of this phenomena, then you can explain it as the thickness, right? That is the general term. Generally, we use the term thickness to explain this type of phenomena. Then bee honey is more thicker than the coconut oil, and coconut oil is more thicker than the water. That is how we identify that. Okay. Then the scientific term used to distinguish this property is viscosity. Okay. So now we can study the properties of liquids. Especially here we will be talking about the flow properties of fluid, of liquid. And you can remember, just give me a minute, okay? Okay, then we are going to talk about the flow properties of liquid, right? Then when you think of the flow of liquid, then you can remember we talk about the flow of fluid, flow of liquid in at the end of mechanics in the Bernoulli's theorem. Okay, now let's try to identify the differences between the properties of the fluids that we discussed under Bernoulli's principle. If you can remember, when we apply Bernoulli's principle to a flow of a fluid, then it is first thing was it must be streamline flow. It must be a streamline flow, and the fluid must be incompressible. Now these are the properties that that must be there for a flow of liquid to apply Bernoulli's principle. Okay. Third one, it must be non-viscous. Non-viscous. Okay. Now here we are going to talk about viscous fluid. We are going to talk about viscous fluid. Okay. Then what is the difference between non-viscous fluids and viscous fluids? Right. Viscosity or the viscous is the property that belongs to the flow of a fluid. Okay. Now when there is the flow of fluid, now for example, if you have no pressure difference across the tube, there is a tube like this, and if there is no pressure difference across the tube, there will no fluid flow practically. But in the Bernoulli's principle, we identified that if there is the flow of a fluid in a uniform tube like this, the pressure at these 2 points, these two ends must be the same. Okay, so that is where That is the role of viscosity. Okay. Now, in the presence of viscosity, the pressure difference is a must. But without the pressure difference, viscous fluid or practical fluid does not flow. Now, we were talking about the ideal fluid in the Bernoulli's principle. Ideal fluid flow is possible under no pressure difference, right? But real fluid cannot flow without the pressure difference. So pressure difference exerts a force, right? Then think of the reason behind the requirement of force. Why a force is required? Because there is a resistance, right? Since there is a resistance, we must apply a force on the liquid to make it flow. Okay. Therefore, the viscous fluid always in the flow exert a force against the motion. Okay. So we are going to talk about that. Okay. And then when we talk about the flow of fluid, you may have heard of two terms, steady flow and turbulent flow. Okay. Then what is a steady flow? Theoretically, steady flow is now when there is a steady flow, every particle or each particle passing to a point to a given point will have the same velocity and it will, or they will, follow the same path. Okay, so this is how a steady flow is identified. Okay, so I think it's better to take down this because this will be important for you. A steady flow is something like this. This is a steady flow. Okay. Then turbulent flow is something, a flow takes place with turbulences. Okay, now I will show you some examples. Now look at this flow. You can see it consists of a lot of turbulences. Now particles are moving here and there rather than going in a straight path. Okay, so this type of a flow is called a steady turbulent flow. Okay, and whereas if you look at the flow like this, Now you can see it's a calm flow. You can see through the water stream. This type of flow is called steady flow, right? Especially this type of a steady flow is a calm flow, right? There is no turbulence, also no any whirlpools. No such things happen. It's a calm flow, okay? And also in your home, you can try this. Look at this. Now, if you have a steady flow from your tap, you can demonstrate something like this. I hope you can see what I'm going to show you. Now here, there is a can under the steady flow, and can you see there is a glass-like thing around the can? Okay, here, that is actually water. Okay, now steady flow of water making something like a bubble around this can, right? Now try this at home. Actually, then you can distinguish the steady flow and turbulent flow. Now, as your speed of the tap increasing, you open the tap more and more. Then at a certain point, your flow will become turbulent, and thereafter you can't make this type of a bubble around the can. Okay, so it's a very interesting demonstration, right? Okay, then when we show a steady flow, generally we use streamline. Okay, in order to show a steady flow, we use streamline, and streamlines of a steady flow don't cross each other. It is going like this. So this is a steady flow. Whereas the turbulent flow is considered, in a turbulent flow, part of a particle, part of a molecule will take complex shape like this, right? It consists of some whirlpools, and they are crossing each other just like this. Okay, so this is the turbulent flow. I think it's better to draw this type of steady flow and turbulent flow. Okay. Then now really this steady flow is twofold. Now we applied the Bernoulli's principle for steady flows. Then the specialty of that steady flow, it was ideal fluid. It was an ideal fluid. Then you can apply Bernoulli's principle. Right? For a steady flow of an ideal fluid, you can apply Bernoulli's principle. What is an ideal fluid? Ideal fluid is a non-viscous fluid. Okay, it has no viscosity, and also it is incompressible. Okay, then if you consider a real fluid means really it is partially real, because now in this case we can't go to the exact real fluid, because behavior of fluid is highly complex, right? Now we are approaching towards real fluids from ideal fluids. Actually, now we are at the intermediate position between ideal fluids and exactly real fluids. Okay, so but we will use the word real fluid, but this is not the type of all the fluids available in the nature. Okay. Then if you consider real fluid, where it is viscous, then such a flow is called laminar flow. Such a flow is called laminar flow. Now I understand this clearly. Steady flow is twofold. If we have a steady flow of an ideal fluid, there we can apply Bernoulli's principle. And if there is a steady flow of real fluid where the viscosity is there, then such a flow is called a laminar flow. Let's try to identify what is this laminar flow is. Okay. Look at this. If we have a fluid with no viscosity, and if there is a steady flow, right? The flow takes place like this clearly. Now, see if you can understand this one. Now, okay, this is the tube. May part of the tube better. And this blue part is the liquid. Now, liquid is coming out of the tube as a bulk, as a cylindrical column. Okay, this is the type of flow we expect in a steady flow of an ideal fluid, because all of the particles causing given cross-section is having the same speed. Okay, but when we consider a laminar flow is a layered flow. Okay, it's like this. Right there, when you consider the flow of the fluid, it takes place as layers, right? Then centermost layer or centermost part of the flow has the highest speed, and then the speed of flow is decreasing gradually when you go from axis to the wall of the tube. Okay, at the wall of the tube, the layer which is in contact with the wall is considered to be at rest. Okay, so that is some of the things still are not real, right? Now, this may not be real for a exactly real fluid, but here under this topic, when we talk about the laminar flow, here we consider the layer which is in contact with the wall is at rest, right? Then the speed increases. Now, generally we used to indicate this type of flow using streamlines, or the speed can be indicated by arrows. Then this type of a flow is generally indicated like this. Let's say this is the end of the tube, and then the speed of the centermost part is the highest, therefore it has the longest arrow, and then the speed will be decreasing just like this towards the wall, and also on the other side speed will be decreasing towards the wall like this. Okay, Okay. I made a mistake. Just give me time to correct it. Okay. This is the nature of laminar flow. Okay. In a laminar flow, the centermost part of the in a laminar flow, centermost part of the flow has the highest speed and the speed is decreasing towards the wall. But when you consider steady flow of ideal fluid, they have the same speed. Now this is again the end of the tube, and all of the particles will have the same speed. Therefore, arrows will have the same length, just like this. This is how we indicate the steady flow when it is laminar flow or ideal fluid flow. Okay. I think again it's better for you to take down this one also. Steady flow is twofold. Sometimes for ideal fluid, we can apply Bernoulli's principle, and for real fluid, it's a viscous fluid. Then we have a laminar flow. Then laminar flow takes place just like this. Right. If you miss anything, you can come to YouTube channel and replay the video and take down what you want. Okay. Right. Now let's try to understand the reason behind this type of layered flow when there is viscosity. Okay. Now viscosity is the factor that causes a resistive force for the motion of the fluid. Viscosity is a factor that causes a resistance to the flow. Okay. Now viscous flow, steady flow of a viscous fluid is always a layered flow, laminar flow. Then let's try to understand how this resistive force is applied on such a layer. Right here, I'm going to draw two layers of fluids which are in contact. So this is one layer. And I'm going to draw the other adjacent layer. Like this. Then okay, I will place them so that we can mark the force clearly, but really these two layers are close to each other. Okay. Now, if you consider a flow takes place on a flat surface, right? Before taking these layers into consideration, let's try to understand how the flow takes place on a flat surface, right? Now, you know, in a cylindrical tube, the flow takes place as layers and cylindrical layers. Then, if we consider the flow takes place on a flat surface, then it will look like this. If I draw it three-dimensionally, now layers will be separated like this. Okay, this is the part of the flow flowing in this direction. Then when this flow is allowed to flow, now the layer at the bottom part, now I will do, this is the base of the flow, the flow bed, and immediate layer with the surface which is in contact with the flow bed is at rest, as we consider, and the next layer will have a slightly higher speed than the first one, and the layer above it will have little bit faster speed, and the above one will be even faster, like this. Okay, so when you indicate this flow with arrows, we can draw it like this. Top one has the highest velocity, so highest arrow belongs to that, longest arrow belongs to that, and next one less speed, less, and negligibly small speed at the bottom. Okay, so this is how flow takes place, real speed flow takes place on a flat surface. Okay, I think it's better to draw this one also. And also it is important to note that the speed of layer in contact with the solid surface is considered to be at rest. Really, it is with respect to the solid surface. Okay, I will explain you the importance of this with respect to part, but for now you must understand this is how we consider laminar flow. When there is a laminar flow take place, the layer which is in contact with the solid is at rest. Really, it is with respect to the solid surface. Okay, that means really if the solid surface is moving, the immediate layer will be moving with the same velocity, same speed as the solid surface. That is the idea behind this. Okay, so this is how a layered flow or laminar flow takes place on a flat surface, right? And in a cylinder, it's cylindrical layer, right? Now let's consider, let's try to understand how this. I think you took down this one. Okay. let's try to understand how this resistive force or the viscous force is acting on a given layer. Right now, I am going to consider two layers which are in contact, but for the convenience of drawing, I will draw them slightly separated so that I can mark the forces acting on them. Okay. Now the top layer has the higher speed, and the bottom layer has relatively low speed compared to the top one, and therefore now consider one more layer. Okay, just like this. Okay, then the top layer is moving faster, therefore it is trying to now this is the kind of drag force, no viscous force is, therefore now the top layer is trying to drag along with it, drag the bottom layer along with it. That means the top layer exerts a force on the immediate layer in the forward direction like this, right? Then according to Newton's third law, for every action there is equal of this opposite reaction. Therefore, there will be a force that is opposing the motion of top layer from the bottom layer. That force, I will mark that force here because I can't mark that under the layer. Therefore, just like this. Okay, so this is the same force F as this one. Okay, these two are equal opposite forces. Actually, they are action and reaction, right? And also, when you consider the third layer and second layer is moving faster than the third one. Therefore, second layer is exerting a force on the bottom layer or the third layer, just like this. I will take it as S dash or something, and its equal opposite reaction will be acting on the second layer, just like this, F dash. Okay, now if you consider the second layer, it has a resultant force, forward F force and backward F dash force. Then the resultant will be forward. Therefore, now the flow takes place forward, and the speed of layers will be different like this, because as we go down in the stream, more and more forces will be, magnitude of forces will be greater and greater. Therefore, layers at the bottom experience relatively large force. Therefore, their speed will be less. So that is why this type of a flow is expected. This type of a flow is expected in a laminar flow. Okay, right. Then our next task is to identify, understand the magnitude of this force. Okay. Now, here in our lesson, we are not going to derive anything from this type of diagram, but we are going to just know the magnitude of the expression for the force and use them in problems. Okay. And but I will briefly explain how this happened. Now, if we consider this force F, right? This F is found to be depend on two factors. One is the surface area. One is the surface area of the layer, right? And the other one is called the velocity gradient. I will explain what the velocity gradient is by taking this one. Let's identify velocity gradient. Now, if we consider this type of a laminar flow, we expect the variation. If we measure the distance d from the bottom of the flow, from the flow bed, right? I'm going to measure d upward direction from the bottom of the flow. Then, if I draw the graph, how the speed v varies with the with d, then it will be a graph like this. Now here I'm going to take v to the y-axis and d to the x-axis. Then we expect a graph like this, a straight line. Okay. Now you may surprise how this variation of velocity is always become straight line, always uniform, and how the velocity at the bottommost layer becomes zero, right? Really, not all the liquids are obeying, are flowing according to this relation, according to this graph, right? Liquids which are flowing according to this graph are called Newtonian fluids. Newtonian fluid. Okay, it's related to Newton. Related to Newton. Okay, then a Newtonian fluid is actually a fluid flow takes place in such a manner that velocity gradient, or this one gradient of this graph, velocity gradient is uniform. Okay. Now I think you take down these diagrams into your note, and then we can write down what a Newtonian fluid is. A fluid that has velocity gradient, that has a uniform velocity gradient in flow, right? If certain fluids show this property, where there is a uniform velocity gradient, then we say it's a Newtonian fluid. So I couldn't mention this one, what the velocity gradient means. Velocity gradient is actually, now if there is delta v change of velocity in d distance, then velocity gradient is delta v over d, really the gradient of this graph. Okay. Now remember that all the fluids are not Newtonian fluids. Newtonian fluids have this special property. They have uniform velocity gradient in a flow. Okay. Sorry. Right. Now we can study what factors that affecting the viscous force. Now it has been found that the viscous force that we discussed earlier is proportional to the surface area of the layer, and also it is proportional to velocity gradient, that is delta V over D. Okay. Now we can build up an expression for the viscous force. Now you know, if F is proportional to both A and delta V over D, then it must be proportional to A, the product of A and delta V over D. Then we eliminate this proportionality sign by introducing a constant eta A delta V over D. This eta is called the coefficient of viscosity. So this is the relationship for the viscous force. This eta is called coefficient of viscosity. Okay. Coefficient of viscosity. Right. Then you can write down this. The coefficient of viscosity, coefficient of viscosity is a constant for a given fluid. Coefficient of viscosity is a constant for a given fluid. Constant for a given fluid and a given temperature. And a given temperature. Okay. So eta is a constant at a given temperature. That means eta changes according to temperature, right? So how eta changes with temperature? Eta increases eta decreases with increase in temperature. Eta decreases with increase in temperature. Okay. Now, eta is a constant for a given fluid at a given temperature, and when you increase the temperature, eta decreases. Eta decreases means now higher eta values means it has higher flow resistance. Low eta value means it has low flow resistance. Okay. Now, for example, when you take some lubricating agent like grease or oil or something, then it has very low coefficient of viscosity. Okay. Right. Now, let's try to understand the difference between the friction and the coefficient of viscosity. Okay. Now, directly you can see friction is independent of the surface area. But here you can see this viscous force is depend on surface area, right? So that is the clear difference between the frictional force and the viscous force. Viscous force depend on the surface area, and the frictional force independent of the surface area. And also when there is motion, that is we use the dynamic friction, then dynamic frictional force is independent of velocity. But here you can see really the viscous force is depend on the velocity. Now higher the velocity, higher the viscous force. Okay, that is another difference. Let's try to apply this relation to a certain situation and try to understand how this type of equation, this type of relation is applied for a problem. Okay. Now, for example, let's say let's consider the frictional force and the viscous force when you are walking. Okay. Now you know. Let's consider a man of mass. Say 50 kg, right? Typical mass. And say his foot has a coefficient of friction. Generally, it is around 0.2 or 0.3. Let's say the coefficient of friction is 0.2, right? Then the frictional force on the man is FL, if you say, maximum possible friction is mu r. That is mu is now 0.2. R is the weight because he is walking horizontally. Therefore, it is 50 G. That is 500. Therefore, 500 into 0.2. That is 100 Newton. Right. So this person, while walking, can have maximum 100 Newton of frictional force. But you know, frictional force is not always at its maximum, but it is always acting to stop the relative motion. Therefore, if the man while walking try to slip, then frictional force comes and stop that slipping. So it can stop up to 100 Newtons of slipping force or external force and prevent the man from slipping. Okay, let's try to understand what happened to this force when something lubricating agent is present on the surface. Now, for example, let's say you are walking on the tile. Then when the tile is dry, you have this much of frictional force. Okay, and let's say there is some water on the tile surface, but this man doesn't notice that. Therefore, he steps on this water. Okay. Then let's think about the viscous force. On man with water. Okay. Now, water has the coefficient of friction, coefficient of viscosity just around 10 to the minus 3, right? Particular coefficient of viscosity order is 10 to the minus 3. Order of the coefficient of viscosity is 10 to the minus 3. And then let's apply, and surface area is affected. So when he steps on his foot, let's say his foot is 10 centimeters long and 5 centimeters wide, then typically it will be around 50 square centimeters. Okay, 50 square centimeters. And let's say he is walking with typical velocity 1 meters per second. Okay, then generally the thickness of water layer when you step on water like this, let's say this is that man's leg. Okay, when he step on water, then there will be a slight or very small layer of water. Typically, it will be around 0.1 millimeters. Okay, and then if you look at use the previous equation, F equals A delta V, eta A delta V over D. If you use that relation, then eta is 10 to the minus 3 and the surface area 50 square centimeters, that is 50 into 10 to the minus 4 square meters. Delta V. Now this is important. When this person try to walk or slip on this surface, the bottom surface, that is the flow, is at rest. Therefore, the layer which is in contact with the flow is at rest, and his leg is the other solid surface. Now, I told you that we consider always when there is a liquid layer in contact with the solid surface, then it is at rest with respect to the solid surface. Therefore, when his leg is trying to slip with 1 meter per second, the layer which is in contact with the foot will be moving with the same velocity. Therefore, now if the thickness of the water layer is 0.1 millimeter, the velocity gradient will be 1 meters per second with the temperature, it is the velocity difference, and those two layers are at 0.1 millimeter distance. Therefore, now we can replace delta V over D by 1 over D is 0.1 millimeter 10 to the minus 3. Okay, now we can do this simplification. Then 10 to the minus 3 into 0.1. 0.1 is 10 to the minus 1. Therefore, these two will compose 10 to the minus 4. That 10 to the minus 4 will cancel off. This 10 to the minus 4 will cancel off this 10 to the minus 4. Then 15 to 10 to the minus 3 comes. That means 0.05 Newton. So in the presence of water, your chance of slipping is very high. Then, as you can see, the force exerted by the water surface or the viscous force is 0.05, very small force. But in the presence of friction, it can exert as much as 100 newtons when it is necessary, right? Maximum possible force not. Therefore, there is a high chance of slipping on the surface in the presence of this type of lubricating agent, water. And if oil is present, this force will be even low. Okay, just like that. So this is how we can apply that relation, and that is how we think of a problem when there is a layer of this lubricating agent between moving objects and surface. Okay, then before going forward, let's try to find out the units and dimensions of coefficients of viscosity. Units and dimensions of eta. Now you can make the eta subject from the previous relation. So let's take down that relation. F is eta A delta V over D. Then make eta subject. Eta is F D over A delta V. Then we can think of units. Units of eta. Force Newton and D is the thickness meters and A is the area square meters. Delta V change of velocity is the velocity ms minus 1. So if you simplify this, you will end up with n s n minus 2. Okay, so unit of eta means unit of coefficient of viscosity is Newton seconds per square meter. Or you can break down this a little bit further to the basic unit. Then it will be Newton will be break down to kg ms minus 2 s m minus 2. Then we will end up with kg m1 m minus 2, that is m minus 1 s minus 2 s minus 1. Okay, either this way or this way we can present units of eta. Okay, then if you consider the dimensions of eta, now it's convenient to use this relation, this unit kg m minus 1 s minus 1. Then the dimensions will be capital M L minus 1 T minus 1. Okay, I hope you are following me on the board. Okay, right. So now we have identified the reason behind the viscosity or the flow resistance and factors affecting the flow resistance, and also the relationship for the flow resistance. And finally, we identified the coefficient of viscosity and the factors that changes the coefficient of viscosity. What are the factors that changes the coefficient of viscosity? The temperature and the fluid itself, right? Different fluids have different coefficient of viscosity. Okay, then we can move into next part. Really, now so far we have only a single relation, F equals eta A delta V over D relation. So that is a relation that you must remember, right? And you can use that relation in problems directly without the proof. And now we can talk about the flow of fluid in a tube. Flow of fluid. Really, here we will be talking about liquids. In a tube. Okay. Now, for this purpose, there is a relation called Poisson's relation. Give me a second. has slightly odd spellings. That's why I said so. So it's okay. Poisson, the word Poisson has slightly odd spelling. Okay, Poisson. This is pronounced as Poisson. Poisson's equation. Okay. Now Poisson found that there are three factors affecting the rate of okay. Poisson found that there are three factors affecting the rate of flow through a tube. Really, here we are talking about the rate of volume flow. Okay, they are first one, radius of the tube. Second one, length of the tube. And the third one is called pressure gradient. Pressure gradient. That is the pressure difference over the tube divided by length. That is delta P divided by, it's a different color. Delta P divided by L, and length of the tube L, and the radius to take as R, right? So these are the factors as found by Poisson that affecting the rate of volume flow through a fluid, through a tube. Okay, really this is not a surprise, because now think of the garden hose in your house. Okay, so when you connect your garden hose to the tap, then if you look at the rate of volume flow or the amount of water coming through the tube, then you will notice that the amount of water coming through the tube will be slightly less than what is coming out of the tap. Okay, now if you remove the hose and open the tap, you can have somewhat higher rate of water flow. But if once you connect the garden hose to the tap, then it will be slightly less, and you can observe it clearly if you have a slightly long hose, right, somewhere around 100 feet long tube or something, hose or something. Then you will notice that really the flow rate is less. That means the length is affecting the rate of flow, right? And also, you know, if you can build up your tank in the house at a higher elevation, then rate of flow will be increased, right? Therefore, the height of the tank actually changes the pressure or the pressure difference. Therefore, pressure difference is also affecting the rate of water flow. That's trivial. And also, if you use a large tube, right, rather than taking a half-inch tube, if you take 1-inch tube, then you can have more water in less time. Therefore, you know, size of the cross section or the radius of the tube is affecting the rate of fluid flow. Therefore, these three factors are not really surprising. They are anybody can understand these are the factors that affecting the rate of flow, right? Then now, according to Poisson, he expressed the Poisson's formula, that is the relationship for the rate of fluid flow, that is the volume of fluid flow or the liquid flow divided by time, is equal to pi r4 delta p over L, pi r4 over 8 eta delta p over L. Okay, so this is the Poisson's formula for the flow of fluid, flow of a liquid through a tube. Okay, proof is not important. You can directly use this relation in a problem, but you must know how to derive this relation using these three factors. Right? If you are given the rate of liquid flow through the tube is governed by these three factors, you can use the dimensional analysis and get the relationship for the rate of fluid flow. So that is expected from you. Therefore, you must practice this, how to derive this relation using the dimensional analysis. Okay, and also sometimes you may you can be asked to prove this relation using dimensions. Then you know how to do it. You can find the dimensions of left hand side separately and right hand side separately. Thereafter, you can show that those dimensions are the same. Therefore, equation is dimensionally valid. So dimensional validity can be asked to check, and also you can be asked to derive the relation using dimension for dimension analysis. Therefore, practice that yourself. Okay, right. Then there are several factors. There are several factors to be satisfied for the Poisson's formula to be applied for a flow of a liquid. Okay, therefore it's better to take down those factors. So factors to be satisfied to apply Poisson's formula. Factors to be satisfied to apply Poisson's formula. Okay, let's take them one by one. First thing is that flow must be laminar flow. The flow must be laminar flow or steady flow. Because now you know steady flow and laminar flow is the same thing. And the second factor, the flow must be continuous. It's trivial, no? The flow must be continuous. Flow must be continuous, right? Because if the flow is breaking down time to time, then it may not be a laminar flow, right? Therefore, flow must be continuous and flow must be a laminar flow. And also, the flow must be, the fluid must be incompressible. Okay. And there is another factor which is very important. The tube. The tube must be horizontal and narrow. Okay. Tube must be horizontal and narrow. So those are the factors to be satisfied to apply Bernoulli's formula. Okay. Especially now, if you consider the a vertical flow of a fluid in a tube, then there is an additional pressure due to the potential difference. Okay, we studied that in the Bernoulli's principle. So therefore, there will be some complications. Therefore, we can't apply Bernoulli's formula, sorry, Poisson's formula for a vertical or inclined tube, right? And if it is a broad tube, right? Now, when the tube becomes broader, then the flow tends to become turbulent, right? This type of laminar flow is not possible in a broad tube. That is why this type of condition is there. Tube must be narrow. Okay, so remember these four factors as the factors that affecting the factors to be satisfied to apply the Poisson's formula. Okay. Right. With that, we can move to the last part of the lesson, theory part. Now, so far, we have learned only two equations. One is the equation for the viscous force, F equals eta A delta V over D, and Poisson's formula. Now we are going to learn the next formula, that is all. Clearly, there are three equations, three formulas you have to remember in this lesson, and there are some conditions to be satisfied before you apply those formulas. And that's all. Such an easy lesson. Okay. Right. Our last topic, the motion of an object. The motion of an object in viscous medium. The motion of an object in a viscous medium. Okay. Right. We know that when we have motion in air, we have talk about the air resistance. Air resistance is a kind of viscous force because air is a fluid. Air is a fluid with viscosity. Therefore, when there is a flow of air or when there is some motion of an object inside the air, then it experiences the viscous force. And also, when you move something in air, it will be quite easier compared to the same thing, same movement is made inside water. Right? For example, if you move your hand in air, then you can easily wave it. But if you try to do the same thing inside the water, then you will feel it's more difficult. Right? That means water is more viscous. Air is more viscous than sorry. Water is more viscous than air. Right? So viscosity of water is higher. Okay, that's the reason. So you must know that now different objects will experience different type of forces. Actually, this viscous force or the resistive force depend on the shape of the object. Okay, I think it's better to write down this as a fact. The viscous force on an object. Write down. The viscous force on an object depend on viscous force on an object depend on the shape of the object. The shape of the object. Okay. With the viscous force in different all shapes of the object will be highly complex. The calculation of viscous force will be highly complex. Therefore, now in our A-level syllabus, we have confined our discussion to the viscous force acting on a spherical object only. Okay, viscous force acting on a spherical object. So you can write down the viscous force as a subtopic. The viscous force on a spherical object. The viscous force on a spherical object. Okay, the magnitude of this viscous force on a spherical object has been discussed by a scientist called George Stokes. He was in 1819 to 1903. Okay, George Stokes discussed about the force on a spherical object moving in a viscous medium. Okay, so you can write down the force on a spherical object. Force on a spherical object moving in a viscous medium. Moving in a viscous medium was first studied by a scientist called George Stokes. Okay, so as a result, today we have Stokes law, right? So according to Stokes law, force on a spherical body moving in a viscous medium depend on first one, size of the sphere, that is the radius r, and the second thing, coefficient of viscosity, eta, and the third fact, the speed. V. Okay, so those are the factors according to Stokes that govern the viscous force on a spherical body. So he said the relation for the viscous force can be given as F equals 6 pi eta r v. Okay. So take down. Then again, just as the Poisson's equation, you may ask to derive this relation using dimension analysis, and also you can be asked to verify this relation using dimension analysis. Okay, so you must be prepared for that. Okay, right. Now again, there are factors again to be satisfied by the motion of the sphere in a viscous medium for it to be applied with the Stokes law. Okay, so you can write down the factors to be satisfied apply Stokes law. The first thing must be the fluid. The fluid must be still, right? Now, fluid must be still and the sphere is moving, right? When a sphere is moving in a moving fluid, it's a complex situation. You can apply Stokes law to find the force, okay? That is what it says. And the second factor, the spread of fluid must be infinite. Infinite, that means large compared to size of the sphere. Okay, the spread of the fluid must be infinite. That means really the spread of the fluid must be large compared to the size of the sphere. Now, for example, you know, if you have let's say there is a cylinder, just like a measuring cylinder, tall one. Then say you have a measuring cylinder like this, and you are going to insert a sphere of this size into the measuring cylinder. Then you know the motion will be affected, downward motion of the sphere inside, let's say this cylinder contains water. It will be affected not only by the viscous force, but there is little room for water to move up above the sphere, so that the sphere is allowed to move downward. Therefore, this type of motion for this type of motion, Stokes law cannot be applied. That is what it says. But if you have say cylinder like this and sphere of this size, then this size, right? That's okay, right? Because now the motion of the sphere may not be affected by the movement of the liquid particles, because there is more room for liquid to move here and there. Therefore, only the sphere will experience only the viscous force, right? So that is the idea. So these are the two factors to be satisfied for a motion of a sphere to be applied with the Stokes law. Okay, right. Then let's try to understand some of the phenomena, some of the consequences of this Stokes law. Now let's consider Consider sphere. It's a metallic one. Metal sphere released into a tall cylinder of water. Consider a metal sphere released into a tall cylinder of water. Okay, let's try to understand the consequences. Say this is the sphere, right? At the beginning, that is at t equals 0. Then we just release the sphere. Therefore, at the moment we release the sphere, the downward velocity is 0. Right? Now let's consider the forces acting on this. Its weight will be acting downward, mg, and since it is inside the water, it will experience the upthrust. I will mark it as u, right? And there is no viscous force at this moment because no motion. Now, according to Stokes' law, you can see F is affected by the speed. When the speed is 0, F is 0. So at the beginning, the speed of the ball is 0. Therefore, speed is 0. Then it will have certain acceleration. Okay, acceleration at this moment. Let's say it is A. Now it will be less than G because there is an upthrust. So G will be, acceleration will be less than G. But I will tell you this now, and later on you can understand this. This is the maximum acceleration. This is the maximum possible acceleration of the sphere, right? When you go to the next situation, you will realize that this is the maximum acceleration. Okay. So let's go to the second situation where after a while, okay, then when you take after a while, now certain velocity has been developed on the ball. So it has some velocity v, which is not 0. Okay, and now the time is t after some time. Then it will have certain acceleration. Let's say a dash. Okay. Now think of that a dash. Okay. The weight of this object is still acting mg, and the upthrust is acting u, no change. But now it has a velocity. Therefore, it will also be experiencing viscous force. I will write it as f theta, right? Now this f theta was absent at the beginning because velocity was 0, but now the velocity, the sphere has developed some velocity. Therefore, it has certain velocity. It has certain viscous force f theta. Okay. Now you can see mg and u are the same in both situations. Therefore, the resultant force on the sphere, in this situation, second situation, will be less. Okay. Therefore, no doubt, this acceleration will be less than the initial acceleration A. So this will be less than A. Okay. So now, if the the sphere still has some acceleration, that means its velocity is increasing. Okay, I think you have taken down these things into your note. Okay, these drawings and everything. So now, even at this situation, if the sphere has a velocity, if the sphere has an acceleration, then that means its velocity is still increasing. Okay. Now we can write like this. If a dash is non-zero, not zero, velocity is increasing, going up. It indicates that f theta is going up. Okay. Now, what about the resultant force from the sphere in this situation? Resultant force, let's say it is F. F is now upward and downward we have mg, and upward we have u and f theta. So the resultant force will be downward, must be downward. That is why we have non-zero acceleration here. Okay. If the resultant is not downward, acceleration will be negative, acceleration will be upward. Therefore, this is the resultant force, and even in this situation, f theta is growing, right? According to this, right? F theta is growing. F theta is growing means now here we have really by rearrange this expression a little bit, you may understand it better. Mg minus u plus f theta, right? I wrote the same expression in a different manner. Now, look at this. If v is increasing, f theta is increasing. That means u plus f theta is increasing, right? Then this difference mg minus u plus f theta is decreasing at the moment. Okay, that means now there will be certain moment where this f becomes zero. This resultant force becomes zero because now this part is growing. There will be an occasion where this part u minus mg u plus f theta is equal to mg, right? I think you can understand what I am going to say. Therefore, right, as the time passes, there will be an occasion where f is zero, acceleration is zero. Okay, so I think you indicated these things. Then you can write down. When the acceleration is non-zero, of the sphere, acceleration is non-zero of the sphere, v is increasing. Therefore, f theta is increasing. Then there will be an occasion. Where the resultant force, on the resultant force on the sphere is 0. Okay, then you can take down this part. And you can say when f equals 0, mg equals u plus f theta. Mg equals u plus f theta. Okay. Now there is a situation where this object, this sphere, has no resultant force, right? If you think of the Newton's first law, in the absence of resultant, object can be at rest or moving with a uniform velocity. Now, an object the sphere has no resultant force while on the move. Okay, therefore, now it will continue the motion with a uniform velocity. Okay. Therefore, this object will be moving with a uniform velocity, after above situation. This uniform velocity is called terminal velocity. Terminal velocity BT. Terminal velocity BT. Okay. Now let's try to get an expression for the terminal velocity. Now you know once it attains the terminal velocity, forces acting on the sphere is given by mg equals u plus f theta. So f theta can be written in terms of Stokes' law, that is 6 pi eta r v. Now it is at the terminal velocity, therefore it is Vt. Now if you make the Vt subject, we have 6 pi eta r Vt is u mg minus u. Then we can make Vt subject. Vt is mg minus u over 6 pi eta r. Okay, so this is the relationship for the terminal velocity, but I don't recommend you to remember this relation. Instead, you can derive this relation easily if you have the idea. Okay, so take the idea and thereafter you can derive this relation easily. Okay. Right. Okay. Now this is a general situation. Now mg, now the sphere can be anything. It can be a hollow sphere or solid sphere. Solid sphere means it may be consist of different materials. Whatever it is, Vt must be given by this relation. Okay. Now let's try to before that, there's one more thing. Now let's consider how the velocity of the sphere changes with the time, right? Okay, about sphere. Let's consider the variation of velocity. Variation of velocity of the object of the sphere with time. Let's consider that. Now, okay, it doesn't work. Okay. Now, the acceleration of this body is variable. Initially it has certain acceleration, but later f theta develops. Therefore, acceleration decreases. Acceleration of VT graph is represented by acceleration in a VT graph is represented by the gradient of VT graph. Therefore, gradient of this VT graph must be decreasing, and at the end acceleration is 0. Then it must be a uniform velocity. Therefore, graph will be look like this, and this velocity is the terminal velocity Vt. Okay, and also you can draw the variation of acceleration with time, how the acceleration changes. I think you are drawing the graph with me. Okay, At. Initially, it has the maximum acceleration, and it has the maximum acceleration, and thereafter it is decreasing. Once it gains the terminal velocity, acceleration is 0. Therefore, it is actually a non-uniform variation. So, it will be a graph like this. Acceleration eventually becomes 0. It will be therefore more curved and finally come to 0 acceleration. This is that A, that was the maximum acceleration. We got early. Okay, then I will leave you to try to draw how the displacement changes with time, and what else? The force, resultant force changes with the time. Those things can be drawn, but I leave you to draw that. You can think of the variation and draw it, because these type of graphs can be asked in MCQs. Therefore, it's better to draw these graphs and have some idea. Okay. Right. Now, the previous relation. This relation is for any sphere that is moving downwards in a viscous medium, and especially if we have, now here we consider the sphere released in water. Therefore, clearly this upthrust is considerable. But if you release an object in the air, if you release this sphere in the air, then upthrust from the air is negligibly small compared to the weight of something like metallic ball, right? Metal ball like a forgetting the same. Then you can omit this upthrust, and then the Vt will be given by this relation, mg over 6y eta r. Right, and so on. You can rearrange this relation according to the requirement, right? But there is a special situation I need to discuss. if we have a uniform metal sphere, I mean uniform solid sphere, okay, then let's consider that. Consider solid sphere of density rho moving really down. Moving down in liquid of density D. Then we can use the previous relation to derive this. We have an expression for this one also. Now we had the Vt as mg minus q over 6 pi eta r. Now this sphere is made of metal of density or certain material of density rho. Therefore, mg therefore, now we can write mg as, okay, let's write down that part. First. Then if you consider metal sphere, its weight will be, its volume, that is 4 over 3 pi r cube rho g is the weight of the sphere, and the after u, it is again the same volume of the sphere, 4 over 3 pi r cube d rho, sorry, dg. So now we can substitute mg and u in this relation. Then we have Vt of that sphere. mg is 4 over 3 pi r cube rho g minus u is 4 over 3 pi r cube dg over 6 pi eta r. Now you can see pi cancels, and also 1 r can be cancelled, then this become r square, and this also become r square. And let's do the simplification a little bit. We have 4 over 3 can be taken out, and r square can be taken out. Also g can be taken out. Then inside we have rho minus d divided by 6 eta, and we can simplify further. 4 r square g rho minus d over 3 into 6 eta. Now this cancels by 2, 3 into 2. So ultimately we will have Vt is 2r square g rho minus d over 3 into 3, 9 eta. This relation. Okay. So Remember now, none of these relations for VT are to be remember by heart, but there may be some advantage when you are going to MCQ paper. If you have certain way of reminding this type of relations quickly rather than deriving to the process, because it takes time, no, right? Therefore, try to remember in certain manner, or try to have some idea to remind it quickly rather than deriving, right? But all you have to remember from this lesson is that three relations for the one for the viscous force and Poisson's equation and Stokes law, right? Those are the three relations you have to remember, and that's all for the lesson, right? So these are the, now I have discussed almost everything I have to discuss with you under the theory. So now I can let you ask some problems if there is something you couldn't understand, or if there were something you have to clarify. You can ask any question. Otherwise, we can wrap up this lesson for now. But I'm expecting to discuss some problems with you in the future. So I will arrange another lesson to discuss problems regarding this lesson, because it's a very easy lesson regarding the other lessons. Theory parts are somewhat broader in other lessons, but this unit, theory parts are very simple. Especially these are really the mechanics type of theories are there. Therefore, they can be understood clearly, and there are no much complicated details in this lesson. Therefore, problems are really easy, and if you take past paper questions from this lesson, you will see that they are really easy. Really, you can easily score about 25, very much close to 30 out of 30. Therefore, I recommend you to study this lesson, including this one, and there are two more topics: viscosity, elasticity, and surface tension, in those two lessons. And remember, last year we had the question from the viscosity. Therefore, it is less probable to have an essay question in this year from the viscosity. But we can't say that for sure, right? There are occasions where consecutive years having the problem from the same lesson, right? Therefore, study these topics carefully and be prepared, because this is a lesson. This is a question that you can score much compared to the much easily compared to the other lesson. Okay, right. I think there are no questions from you, right? Therefore, I'm going to wrap up the lesson. Before we end, I can give you my contact number, WhatsApp number. So if you have any doubt, or now I'm planning another lesson for you with the problems from this lesson. Therefore, if you have any suggestion, just send those suggestions to me. Then I can make the lesson, make the session for the questions according to your ideas. Therefore, I will give you this number for you. That is 071-800-1514. This is my contact number. You can call me or you can text me through WhatsApp or something for any suggestions. So if you don't have any question, I can hand over to the Nanopower Foundation. Before that, I want to thank Nanopower Foundation and also Mr. Nandita for doing this valuable job for you. And also, I ask you to do your part. That is, now you had this lesson and you participate this lesson and you got something from the lesson. Therefore, your task to admire the people who behind this task, the Manpower Foundation and especially so you can text them and you can go to the YouTube channel and leave a comment thanking them for continuing this type of valuable service. Okay, right. So then I will hand over to the staff of the Manpower Foundation. Thank you very much.
Thank you so much, sir. ඇත්තටම අද ෆිසික්ස් කරනට ඒගොල්ලන්ගේ කරපු පාඩම් ඒගොල්ලන්ට නැවත වතාවක් හොඳේ මතකේ රැඳෙන්නේ නැති මතක් වෙන්නේ නැති ඔයගොල්ලෝ උසස් පෙළ ලං වෙලත් මේව බලන්න. ඒ වගේම කියන්න ඕනේ අද දේශනේ ඔයගොල්ලන්ට අපේ නැනපොර YouTube channel එකෙන් බලන්න පුළුවන්. මතක් කරලා අපේ නැනපොර YouTube channel එක subscribe කරන්න. bell icon එක click කරොත් ඔයගොල්ලන්ට ඉදිරි දේශන බලන්න පුළුවන්. ඒ වගේම කියන්න ඕනේ ඉදිරි දේශන පිළිබඳ අපි link යොමු කරන්න අපේ Telegram group එකට. ඉතින් Telegram group link එක අපේ YouTube channel එකේ තියෙනවා. click කරලා අපේ Telegram group එකට සම්බන්ධ වෙන්න. එහෙනම් නැවත වතාවක් අද අපිත් එක්ක එකතු වුණු අපේ ආචාර්ය සුරේෂ් වෙන්න කොන්සර්ට් අපි හදපිරි ස්තුතිය පුද කරනවා. එහෙනම් අපි තවත් දවසක තවත් දේශනයකින් හමු වෙමු. බොහොමත්ම ස්තුතියි.
වාණිජ, විද්‍යා, කලා, ගණිත, තාක්ෂණ වේදය, විෂය ධාරාවන් වල සියලුම විෂයන් සඳහා දැන් නැනපවුර YouTube channel එක ඔස්සේ නැරඹිය හැක.